Hi, in this video, we want to take a look at the Weibull distribution. Okay, the Weibull distribution it looks visually, if you look at the density, it's similar to a gamma distribution, but it's a little bit different. And it's frequently used to model the lifetime of objects and time between failures in engineering, also in survival analysis. It's especially useful in weakest link situations. All right, so here, this is used primarily when there's like multiple ways for something to fail. And if one thing fails, the whole composite item fails. So think about your car. If your alternator fails, the car is done. If the fan belt fails, the car is done. The tires fail, the thing is done. Now, the gamma distribution also models time till failure, but there we're talking about like the nth failure where we have independent events for the time between failures. So if we were going to talk about like, we want the distribution until like the 5th time and, there's a problem with the machine, that would be gamma. If I want to model until the next time that one or more components fail, that would be Weibull. All right, now the distribution looks pretty ugly. When we take a look at it, there's a lot going on there. Focus mainly on the cumulative distribution function. Okay, so the cumulative distribution function, if you're not used to mathematics, it looks like a lot, but really it's just 1 minus an exponential, and we've got 2 parameters going on. Now, if you think about this, if you let x get super big, e to the power of something, anything that's big, is going to be big. If I take a reciprocal with that negative sign, it's going to be very close to 0. So we can see that as x gets super large, this goes to 0, and the cumulative distribution function as a whole goes to 1. Also, if I plug in 0 for x, then anything to the power of 0 is 1, and the cumulative distribution function gives me 0. Okay, so remember, the connection between the cumulative distribution function and the density is if I take the derivative of the cumulative distribution function, I'll get the density. Okay, so if you basically look at the cumulative distribution function as the baseline for this one, and then take its derivative to get the density. That's the best way to look at this. Now we've got 2 parameters going on this. So first one we have is scale. And here you'll notice that scale divides x. And then shape is the exponent on the x term with a little bit of a twist on it. So here you can see that the exponent of x is beta, if I was to go ahead and just handle exponents and fractions properly. And here I've got exponent of x is beta minus 1. And that minus 1 is because of some derivative aspects. Okay, so it's, that's really what's going on. Now, what's our expected value? Our expected value is alpha, that is the scale, times gamma of 1 over beta plus 1. Remember that shape is beta. Okay. Now, the variance, once again, we have the gamma function. So it's going to be gamma of 2 over beta plus 1 minus gamma of 1 over beta plus 1, all of that squared, and then the whole thing gets squared by alpha squared. So and there's a lot going on there. There is a lot. Now, it works out that if we were to set beta equal to 1, if I look at this, if beta was equal to 1, this x term would disappear. This exponent would be 1. We don't worry about exponents of 1. Those disappear. And we see that what would happen is that this would actually be an exponential distribution. Furthermore, if x is a Weibull random variable with beta shape parameter, then x to the beta is an exponential random variable. And that just comes from doing like a u substitution on here. All right, so now the expected value of the Weibull distribution. Okay, so if I want to take an expected value, remember I take x times the density, integrate over the entire possible domain, and I got it. Now, there's going to be a little bit of a trick here. So this is going to be a very calculus heavy expected value. My trick here is I'm going to do u substitution. So remember that U substitution is reversing the chain rule. And so if you think about the chain rule in terms of the derivative of the inside, I'm going to have to undo that. So something that's going to be very important in a moment is that I'm going to say that U, when I do my U substitution, is x over alpha to the power of beta. All right, well, if I just work with, if I solve for x, I see that x is going to be equal to alpha times U to the 1 over beta. Okay. Now, if I look at this part, if I take the derivative of x with respect to u, so here the left becomes dx du, the right-hand side I have to take the derivative. All right, well, that just ends up, so, this is just a u to the power of something. The power rule for derivatives is the, one of the easiest formulas, and so we get that. Okay, so what we're going to do for our integration, I'm going to start out the standard way, x times the density over the entire range of possible values. All right, so now here I'm just simplifying things up. I notice I have an x and I have an alpha here. So I go ahead and pull them into this parenthesis, which will increase this exponent to beta right there. This beta stays put, nothing happens. And then the e stays the same. Now, here I'm going to do my u substitution at this point. All right, when I do this, I'm going to go through everywhere I see an x to the alpha, or sorry, x divided by alpha to the power of beta, I'm going to replace it with a u. So this part is going to be replaced with a u. This part is going to be replaced with a u. So I'm going to have beta u to the power of beta e to the negative u. Or sorry, beta times u e to the negative u. And then I've got some other stuff to worry about. So if you think about that, if I replace this parenthesis and this parenthesis with a u, and then including the beta, then it's going to be a much simpler integral. But there's still some more work I have to do. So remember, I said that u substitution is reversing the chain rule. Okay, remember that I always have to, when I do chain rule, I always take a derivative of the inside. Well, u substitution, the reverse of that is that I have to take the derivative and I have to make some adjustments. What I'm going to do, I'm going to replace this dx with this stuff I have here times du. All right, so you can, it's not mathematically correct, but it's okay to think about it this way in this course. And if you get into higher probability and measure theory, this is incorrect, but it's okay to think of dx equal to this stuff times du. And so here, I have the stuff I talked about previously up here, and this is the part that corresponds to dx. Okay, so now I just want to simplify everything. I see that my betas cancel out. I see that I've got a u. I have a u to the 1 over beta minus 1. So I know that there's going to be some simplification. The negative 1 is going to cancel out with this u. The e to the negative u is going to stay the same. This alpha is going to stay put, and of course we just get du. All right, so now this is looking a lot simpler, right? I mean, compare this integral to this one. This one looks a lot easier to work with. Okay, so now when I look at this, I notice that, well, that's a constant. I can go ahead and factor that out. And then when I get to here, I realize that, hey, that looks like something from the gamma distribution. Sorry, the gamma function. That looks like the gamma function. And it is, you would be right. So here, this is alpha times gamma of 1 over beta plus 1. Boom, we got it. Now, let's move on to the variance. The variance is going to be the exact same u substitution, but it's going to be a little bit trickier because instead of taking expected value of x, I do the expected value of x squared. So it's a little bit more cumbersome. All right, so what we're going to do to get the variance, I'm going to use a formula of expected value of x squared minus the expected value of x squared on the outside. Okay, so I know what this part is because we just calculated it. This part I need to figure out. So I'm going to work on this expected value of x squared. Now, here, I'm going to go x squared, multiply by the density. And so I look at this, and I realize that once again, I have an x, I have an alpha. I pull it into here to get x over alpha beta. Now, when I'm looking at this, I'm going to do exactly the same U substitution. Now, it takes a little bit more work because I have this X term here. But otherwise, the dx gets replaced by the same thing. This part gets replaced by the same as before. This I have to just replace with, I replace with alpha times u to the 1 over beta. All right, and when I do that, and I went ahead and I just skipped some steps. I didn't show them because it's tedious. This is going to be u to the power of 2 over beta, e to the negative u. Now I look at that, and that is a gamma function again. So boom, I'm just going to go ahead and say, hey, it's gamma function. All right, woohoo, and compute that out. All right, so now what I'm going to do, I'm going to compute the variance using the standard formula. I take this part, I put it here, I square this part, and I put it down here. Now I notice that when I do that, remember when I'm squaring, I'll have an alpha squared and I'll have an alpha squared. So I went ahead and factored out the alpha squared, and that gives us our variance. Now that's not very informative. Honestly, it's pretty ugly, but that's what it is. Now, the Weibull distribution is very useful for things like in survival analysis, failure times, weakest link situations. So that means that we're very interested in the failure rate function and the hazard function. All right, so remember, the failure rate function is just the density divided by 1 minus the cumulative distribution function. All right, so what I'm going to do, I'm just going to go ahead and plug those in. All right, so I notice, so remember, I've got a 1 minus the cumulative, and the cumulative distribution function has a 1 in it, so there's some cancellation with that subtraction, and I'm just left with the E term. Now with the density, I just go ahead and slap it in, and I notice I've got an E, and I've got an E, those cancel out, boom, I've got this. So now, how can I use this? Well, if it looks like I have a hazard function, if I'm in a real life situation, it looks like the data I'm getting gives me a hazard function that looks like a monomial, polynomial with just one X term in it, then there's a good chance that I'm dealing with something that has a Weibull distribution, where the exponent corresponds to beta minus 1, and then I can fit the alpha based off the data that I see. All right, well, the Weibull distribution is a common distribution to be working with, and so far it's in the R pack, it's in R. And once again, X and Q are vectors of quantiles. P is a probability vector. N is the number of observations we want to randomly generate. And we have shape and scale. These have to be positive. And the default for scale is equal to 1. And so if I go ahead and I plot this, so to plot the density, I just need an X, and I need a shape and a scale. And I just picked 2 because they're relatively simple. We plot it, and we can see it kind of looks like this. Now you'll remember that that looks a lot like a gamma distribution also. Visually it does. There is a difference though. Now there are advantages in the Weibull distribution that we don't have with the gamma. Specifically, that if we take a logarithm of it, we have ways of fitting that distribution to data that are not as easy with the gamma distribution. So, there's some definite advantages to the Weibull. Now, the cumulative distribution function, well, here, just like in everything else in R, we start with a P, then the name of the distribution, and we plug in what we want. And here we can see what the cumulative distribution function looks like. Notice that it is skew right. And the quantiles, standard. And then we get random number generation. So if I'm dealing with the time between events, then I'm probably going to be using an exponential distribution. If I'm looking at the time till the nth event, where the time between events is independent, identically distributed, then I'm looking at using a gamma distribution. If I'm looking at a time until failure, where failure comes from a weakest link situation, then I'm probably going to want to use the Weibull distribution. All right, well, that's all I've got for you. Take care and goodbye.